Okay, welcome back. This will be the last part of this introduction to pulsar searching and why we want to do pulsar searching and how we do pulsar searching. And so in this last part, I want to talk to you a bit about why we should search for more. And in this little graphic here, you can see a range of different topics of why pulsars are particularly interesting. We might be interested in studying the emission physics. So how do these pulsars actually shine? And what are the physical processes that make the radio, gamma ray, optical, X-ray emission that we see? And those, because these environments are so extreme, they can tell us a lot about things that we just can't test elsewhere. Similarly, we can look at the extreme magnetic fields and the influence of those magnetic fields on the evolution of the system, how they interact with the star itself, and of course, how they interact with the emission. We can look at binary and stellar evolution. How do these systems form? How do they evolve? All that sort of stuff about how they get their spin and those sorts of things. We can use them to study gravity. We can study whether Einstein's theory of general relativity is the final word on gravity, for example. We can also try and understand the physics of the supernova, the explosions which actually generate these neutron stars. What is the process by which these stars explode, and what is that process related to what's left behind? And then, of course, there's the physics of the interior of these objects, the super dense matter, and what does that tell us about particle physics and also for the formation, evolution of these neutron stars themselves. So I'm just going to take two examples of this, and I will talk in more detail about the gravity and super dense matter aspects of these tests. So why do we want to search for more? So here is a diagram which is called the period derivative diagram. And it turns out that if you measure the period of the pulsar and the rate at which that period is getting longer, you can get two important measurements about the pulsar. We can make an estimate of how old it is, and you can see lines here of constant age, so 10 to the 3 years, 10 to the 5 years, 10 to the 7 years. And we can also measure its magnetic field strength. So that is these lines going in this direction, the dot dashed lines, and you can see they range from 10 to the 10 Gauss down here, all the way to 10 to the 14 Gauss here. And also you can see other lines here which show how much energy is available to this object from the fact that it's slowing down. If we put pulsars on this diagram, then they group in convenient little groups. And let's just go through those in a bit more detail. The ones we're most interested in here are the millisecond pulsars. That's what we're going to use to describe the tests of gravity that we're going to do, and also the tests of general relativity. Oh, sorry, not general relativity. We won't touch on that today, but the tests for supernuclear density. But the young pulsars, the magnetars, the normal pulsars, and the double neutron stars are all very useful for all sorts of different aspects of studying physics. But we're going to concentrate on the millisecond pulsars here because they are the most stable clocks that we know about. And they spin very fast, and usually they're in binary systems. So I touched on this previously, and you may remember some of this from the previous presentation that I gave to earlier cohorts. But just, I think it's worth reminding you of this capability that we have of using pulsars to try and detect gravitational waves. So you've probably heard about the detection of gravitational waves using LIGO and Virgo. And how that works is that you have these perpendicular cavities down which lasers are fired. These lasers bounce back off the mirrors, and then the returning laser signal is correlated. And any changes or apparent changes in the length or the distance traveled, I should say, not the distance traveled by the laser beams, causes a change in the interference between them. And this is evidence potentially for the presence of gravitational waves. for the pulsar case, instead of using the mirrors and the lasers, what we have is a pulsar, and we have a telescope on Earth, or many telescopes. In fact, we use many telescopes, and we in fact use many pulsars. But let's consider now just a pulsar and the Earth for now. And so the pulsar and the Earth, if there's a gravitational wave that passes, then it affects, because gravitational waves travel at the speed of light, as we think they do, the gravitational wave that crosses the location of the pulsar will arrive either earlier or later at the Earth. Okay, and so the signal between the two is not correlated. However, if we look at many pulsars, then if the Earth is affected by the presence of the gravitational wave, then we can compare the times of arrival of the pulses from all the different pulsars, and hopefully we can detect the change in each direction, do an analysis, and see that the gravitational wave has passed across the Earth, because the gravitational wave will change the time at which the pulses arrive due to the distortion of space-time. And that's what we say here. The relative motion of the masses is monitored by observing the Doppler shift of the pulsar arrival times. Okay. Now, we expect to be able to detect frequencies of gravitational waves which depend on basically the length of the data span that we've been observing these pulsars for. So anything from about a year up to the longest monitored pulsars used for pulsar timing arrays now are of the order of 20 years or so. So they're in the so-called nanohertz regime, so 10 to the minus 8 or 10 to the minus 9 hertz. So what is the origin of such gravitational waves? Let me first just explain, show in a bit more detail what I mentioned before. So here you have two objects, two black holes in this case, that are orbiting each other. They generate the gravitational waves highlighted by these curvatures moving out. Remember, this is just a cartoon. And you have your pulsars located here and here. And you can see that the gravitational wave is in a minimum here for this pulsar and a maximum for this pulsar. But what we can compare is how the Earth is affected. Okay, and we would see a correlation between the effect of the Earth with this pulsar and with this pulsar, or an anti-correlation, depending on exactly how the pulsars are located relative to the Earth and the source of the gravitational waves. And here's just a comparison. These arms, you can think of them as being like arms of your gravitational wave detector, which is what I was just explaining. So here's an animation which shows what we're actually interested in. So here we were showing two galaxies merging with each other. And we think that most galaxies have black holes at the center of them, and that when these galaxies merge, eventually the black holes will go to the center of this new galaxy, and they too will orbit each other and then eventually merge. And these supermassive black holes, they orbit each other and generate gravitational waves. And those orbits are, we can detect the gravitational waves from those orbits when the orbits are similar to the length of our data span. And you can see here in this graphic or in this cartoon, you can see the color of the pulses changing from red to blue to red. As the gravitational wave crosses over us, this is showing you the change in the arrival time of the pulse from the pulsar. Okay, and so this is what the gravitational waves do. And so by detecting these gravitational waves, we can understand more about how the universe formed, and or at least how the universe got to its present state. And there's two different models for how this happens, right? So if we look out into the universe, what we see are galaxies, lots of galaxies, But we also see these galaxies are arranged in clusters of galaxies, so they're grouped together. And then these clusters of galaxies are sometimes in superclusters. And the question is, how did this happen? Is it the case that, you know, superclusters formed first, then the clusters, then the galaxies, and then the stars? Or did the early universe start with gas and clouds and stars and galaxies? And then the galaxies then attracted to each other to form clusters, and then the clusters attracted to each other to form superclusters. So we've got a top-down or a bottom-up. And we think that the bottom-up approach is the most likely one. And what we think here is that we have, we have these black holes in these galaxies at just not that long after the universe formed, so maybe 200 to 500 million years after the universe came into existence. And then as those galaxies merged, as we can see here, we get these black holes falling into the bottom of these galaxies and potentially merging together to make even bigger black holes. And so that's how we end up with supermassive black holes. And so the question is, does this really happen? Is this what we really expect to see? And the only experiment presently that can search for these and prove that we have lots of these in the history of the universe, we've had lots of these mergers, is the gravitational wave detection using an array of pulsars, the so-called pulsar timing array. So that's a really exciting project, and some really nice results have just come out of that from the so-called International Pulsar Timing Array, which I can direct you to if you're interested. So again, we're going to go back down to the millisecond pulsars, but also to the young pulsars when we think about how we can do studies of the material that makes up the neutron stars themselves, the so-called neutron star equation of state. So we want to look at the exotic physics of the neutron star interiors. And why is this interesting? Well, you may remember that I think I told you before that neutron stars have a mass of around about 1.5 times that of our sun. And it's compressed into this sphere of radius of just 10 kilometers. And so the density is incredible. And if we have 1 teaspoonful of neutron star material, then it weighs the equivalent of 1 billion elephants. Okay, so if you could get 1 teaspoonful of this material, it would weigh the same as 1 billion elephants. And so that's incredibly dense material. And it's just, you know, it's just not possible to study that material with experiments here on Earth. And here is a sort of a cutaway version of something that I showed you similarly earlier. Now you can see this is sort of a cut through of a neutron star. It's a cartoon. And you can see the different densities. So we've got density of 4 times 10 to the 11 grams per centimeter cubed in this outer crust region, where we have these crystal-like crust made up predominantly, again, of neutrons. And then we've got this region in here, which gives us the pasta phases, as I mentioned, where the density is now 2 times 10 to the 4 grams per centimeter cubed. And then we get into this region, which is the outer core. And in the outer core, we have individual protons, and the material is 95% neutrons in here, okay? And you can see that what's shown here are the up and down quarks. And then in the inner core is where we really just don't know what's going on. We don't know if there's quarks just floating around in here, or strange baryons, or something we've just not even thought of. And so if we can get constraints on the radius and the mass of these neutron stars, then we can get their equation of state and their moment of inertia, and that can tell us a lot about what models fit. Okay, so here's a plot on the right-hand side that is slightly complicated, but I'll just walk you through it. Here we see the radius of the neutron star, and here we show the mass, okay? And I'll go through the dark purple lines first. So the 716 hertz corresponds to the fastest spinning neutron star we know about right now, okay? So that rotates 716 times a second. So every 1.3 milliseconds, this 10-kilometer sphere has rotated once. And what this line corresponds to is it says that basically, if this object had this radius and this mass, then we would expect the object to basically fly apart. Okay, so this is a constraint based on that. Okay, and so basically any model for this says that you can't be below this line. So if we were to find faster and faster pulsars, we would rule out all of these lines. So these lines here, these curved lines, all correspond to different models for the pulsar. So models of what this looks like, the interior of the neutron star. And you can see that this is saying that the mass and the radius have this complicated shape in many of these cases. Okay, and so once you measure, what you can see here already is that many of these models do not allow masses of 2.5 solar masses. So if we measure a neutron star with a mass of above 2.5 solar masses, we rule out most of these models. If we can get a radius and a mass, then of course we put a dot in this plot and it can rule out or rule in different models. And so that's the aim of these studies. And so here I'm just showing you again, this is the fastest spinning pulsar. This gives us this constraint that I'm showing here. And so we can measure the masses of these neutron stars. And I won't go into great detail here about how we do that. You can ask me if you're interested later on. But here is a plot showing you all of the masses, all of the masses of the neutron stars that are currently known. And you can see that they all pretty much lie within this range of 1 to 2 solar masses. But there are some very interesting ones here, like this one, who's, looks like has a relatively large error bar, but it looks like it's more than 2.5 solar masses. There's 2 here with quite small error bars that are definitely above 2 solar masses. And so there's evidence that there are at least some neutron stars with more than 2 solar masses. And so we can take these masses and we put them on this graph. And again, as I said, they rule out different equations of state for the neutron star material. So I hope I've given you some idea of how we go about searching for pulsars and why we might want to go and search for pulsars. As I mentioned, there are 3 main ways to find radio pulsars, and each has their benefits and disadvantages. So most modern pulsar surveys are trying to use all 3 approaches so we can fully sample the population. There's a choice to be made when you do a pulsar survey between targeted searches and all sky or blind searches, and it really depends on what your goals are as to which of these you go for. And then I touched on just a couple of reasons why we should search for new pulsars. There are dozens more. If you're interested in knowing anything more, please do ask me questions either after this talk or in the Slack channel. I'd be very happy to try and answer anything. So thanks again for having me speak to you today. And again, I'm very sorry that it's not possible for us to meet in person, but I hope that might be possible again sometime in the future.